Looking at test 7, okay? Test 7.
You just said you would test. Oh.
Now, it was 5-5, and then 6-1 through 6-4. Okay, 5-5, and then 6-1 through 6-4. Can somebody jog others' memories if we don't remember? What was 5-5 about? What was 5-5? Georgia.
It was about, I don't know, but I did the problem so far.
You did it last night.
So what was it about, Georgia?
It was like dividing fractions, and then there was a lot of factoring and dividing, and
Yeah.
multiplying and
Alright, so multiplying and dividing.
Rational expression.
Yeah, fractions are rational expressions. Very good. Okay, so if we remember, let's go through an example that we can see one example of so we have an idea of our steps. So let's say, for example, that we have x squared minus 4 over x squared plus 5x plus 6 divided by, let's see, x squared minus 4x minus 12. Let's make it a, we'll leave it. Let's make it a positive 4x there in the middle instead. And that'll be over x squared plus 3x. Okay? So if we had an example such as the one on the board, this is for 5-5. If you can do an example like this, for the most part, you're good to go on 5-5. Okay? What do we do to begin? What's the first step? First step, Hannah.
You switch the division sign to a multiplication sign, and then write the first fraction as it is.
As it is, good.
And the second fraction, you just flip the denominator and the
Numerator?
numerator. Yeah.
That's right. Very good. So please, you're only switching the second fraction. Why is that? Why are you not switching the first fraction? Who can explain that part? Why are you not switching the first? It would, but it would not make it right, obviously. But what about it is wrong, or what about it do we know?
Because division is not.
Good thought processes of switching, but that's not the reason. But good thought process. I like that idea. Why are we not switching the first one? What is division defined as? Multiplying by the reciprocal. Not taking the reciprocal and multiplying by what you have. Okay? Remember, the definition of division is multiplication by the reciprocal. So whenever you have division, you are still using the first term and multiplying it by the reciprocal of the second term only. Now, it may be tempting to start canceling out my x squared, right? But why can we not do that? Yeah, these are add-ins. They're being added to other numbers. What do we need to have in order to cancel, Austin? Yeah, very good. We need factors, things that are multiplied by other ones or other expressions. So what do we got? Arthur, give me something here.
We can simplify x squared minus 4 to x minus 2x plus 2.
Good, that's difference of two squares. See how easy the factoring is getting, by the way, as you go throughout the year?
And then the bottom,
Okay.
bottom you can do x plus 3,
Mm-hmm.
and then x plus 2.
Very good. You want to go the whole way?
Sure.
Go for
And the top one you can factor out an x, and you get x plus 3.
Good.
Yeah.
GCF, right? GCF, always look for that.
And then at the top you can get, I think, x minus 6. And then, x plus 6, yeah. X minus 2, yeah.
There it is. Okay.
And then,
And then, hold on. Let's pause for a second. Do we all see the factoring part? Are we good on that? Dots, regular factoring, and then GCF with the x, parentheses, x plus 3. Dots, difference of two squares. Yeah.
Whoa, with the app.
What do we do next? I've used dots like 30 times this year at least. Difference of two squares. Yeah. Technically it's difference of two perfect squares, but
Why we say
You learn later that you don't need the word perfect.
Dot it out, dot it out,
Dot.
Oh my god.
That's weird. Worth, what do we got?
Okay, you can cross stuff out.
All right.
Because now it's no longer addition.
What? Yeah, let's explain. Why can we cross, ladies? Stop. Why can we cross stuff out?
Because it's only multiplication.
Yeah, and take a look, folks. When you multiply two fractions, you're really multiplying the whole top. And you're multiplying the whole bottom. So really, this is what we have. Take a look. Just extend the fraction line, really. And then if you just put parentheses around there, and put time symbols in the top and the bottom. It's the same thing as it's not a division sign. Sorry. It is not a giant division sign. You can see it does look, right? So think about it as multiplication in the top and the bottom. That's why you can cross cancel as well as vertically cancel. Now vertically canceling is obvious. These x plus 2's, it's obvious to cancel those. But it may not be obvious to cancel the x minus 2's in the top left and the bottom right until you write it as one giant fraction. Okay, but then we're going to see we can do that. So continue, Worth.
So yeah, then you can cross the quantity x minus 2 off.
Good.
And the quantity x plus 3.
Good. Leaving behind.
X over x plus 6.
Okay, which we cannot simplify any further. Liam.
So if you could do an example like that.
If you could do an example like that, you're good to go on 5-5, yeah. I mean, it might just start with multiplication and it'd be even easier. You don't have to flip it. But for the most part, that's pretty easy. Now, there was one question that somebody brought up. What if you have three things?
Yeah.
Right, remember that question? What if you have three things? I'm going to show you the beginning of that. I'm not going to go through the whole process, but just to discuss if there's a difference or not.
So like
Okay,
if,
so
it's
I'll-
like if the middle one is like 5xy.
Yeah, so let's take a look at one of those real quick before I take any other questions. And this is completely hypothetical. You don't have to actually finish it off. But let's take a look. What if we had xy squared z over xy divided by x squared y over z times z squared yx over x squared. Okay, something like this. Now, please be careful. You only flip the, I don't want to say factor, but it is a factor. You only flip the factor, meaning this middle part, that is directly after the division symbol. Is that clear? So the only thing that's going to be flipped is the middle part of this operation. It's not an equation, an expression, I guess is fine. Okay, so only this middle part right here would be flipped. Okay, only the middle part would be flipped. Ida,
Oh, no.
was that the question you had?
No, I was gonna ask if it's in parentheses, but then you have.
Well, that's what I was going to say next. That's a really good, you're thinking exactly what I'm thinking there, Ida. What if the second and third part had been in parentheses like this? Follow-up question, not the same question. What if it had been like this now? Yeah, because you're dividing by the entire quantity. So you need to flip both of them now. Again, because you'd be dividing this part in the beginning, right here, by the product of these. So technically speaking, you need to multiply these first. So put them all over one fraction line like that. And then you have to flip the whole thing. Okay?
So you multiply them together and then the answer.
You flip it. Exactly. Okay? If it had been in parentheses. Without those parentheses, though, you would only have flipped the middle portion. Okay? Only the middle portion. And I highly recommend that you simplify things before you go any further, like multiplying across, right? So like this x and this x squared can reduce. This x and this x right away reduce them. They both come off. Okay? So depending on what you have in the problem. Simplify wherever possible. The same thing holds true for when we simplify radical expressions. When there's radicals, if you have something like radical 75, you should break that into 25 and 3 right away and make it 5 root 3 or 5 radical 3. Okay, and not work on multiplying because then your number is going to get much larger and then it's going to be difficult to simplify. So try to simplify anywhere you can initially and then go on with the problem. Okay? All right. Questions on 5-5.
What were you saying? So like we could cross out the x squared and the x.
Yeah, so like this here and this here cancel to start, right? This can be canceled with one of these, so that's gone. And then I can proceed with the rest of the problem. Okay? Then I can start trying to cancel other stuff out along the way.
Wait, can you cancel the y and the y squared and the
Yeah, absolutely. Sorry, I didn't even see that. Cancel that with the one term there, leaving behind that YZ in that spot only.
But could you like,
Okay.
if you have like, could you cancel like here and here, like that?
Sure, but not until you rewrite this as multiplication. Yeah. When you write it as multiplication, then start canceling. Technically speaking, if you realize that these will eventually be on the bottom, you can start canceling initially, but rewrite it to make it easier on yourself, okay? So you don't see that misconnection there. Yeah, Liam.
So if the division sign and the multiplication sign switched, would we multiply the first two terms together and then divide that by the last one?
Yeah, exactly right, good. So multiply the first two and then flip the third one and then just multiply it instead, right? Take the reciprocal of the third and then multiply it. All right, let's go on to 6-1, okay? 6-1. 6-1 was, I thought, a relatively easy section, but the difficult part was remembering your perfect squares, your perfect cubes, and knowing how to break up those radicals, how to simplify them. And then 6-2, 6-3, and 6-4 kind of lead or follow 6-1 from there. So, quick example. If I asked you to take the square root of something like negative 16. What's the square root of negative 16? Yeah, it's not a real number. Good. And we haven't gotten into imaginary numbers yet, which we will in the next or after this test. But this would be no real solution. But if you had the square root of 16, Dave, it's just 4, okay? And remember, when you're just asked to take a square root, we're assuming you're looking for the principal square root. So although we know that negative 4 squared does indeed give me 16, we just answer with 4. It's when you solve an equation like this. If this was the equation, and you added the 16 over, and then you took the square root, the answers are plus or minus 4. Again, remember, because this is x squared, so how many solutions should there be? There should be 2 solutions. So when solving an equation like this, you can do this, remember, 2 ways. There are 2 ways to answer. These are 2 separate problems. Just want to show you the difference. Either you can answer this problem by factoring like this, and then coming up with your solutions of negative 4 and positive 4. That's one way to solve that equation. The other way is to add the 16 over, take the square root of both sides, but recalling that you have a plus or minus because there are 2 answers to this equation. So x being plus or minus 4. Either way, it's the same answer. Writing them separately by factoring or writing it with a plus or minus sign in the front. It's the same thing. But again, notice the difference. Up here at the top, this is just asking for the square root of a number, meaning find the principal square root. Whereas down here, you are solving an equation. Okay, you are solving an equation. Let me pick a different color for today. Oh, a lightsaber. You want to use a lightsaber?
Yeah.
All right. And then actually, look, you put it down, and then the lightsaber actually appears.
Oh, that's so...
Let's use the lightsaber for today. We'll point.
Yes.
So again, this answer seems like it's the same thing, but this is an equation down here that we're solving, so there are 2 answers to it. All right, let's keep going with section 6.1. There's more to do. What if we've got the cube root of negative 64? Before giving me the answer, can you tell me what you're physically looking for? What are you trying to do? What is your mind, how is your mind processing this question? Yeah, you think of 3 spots. Good. Why is it 3 spots that we think of? Because if we look at the index, good, and it's a cube root. And then what do we do with those spots? What do we think about next? It's going to be a negative number, good, because remember the conjecture that we came up with that said if the index is odd and you have a negative under the radical, these answers are all going to be the negative numbers. When it was an index that was even, it was no real solution right away. So they're all going to be negatives. Good, so we're going to have a negative, and another negative. What number is going to fill in that spot? Yeah, because again, 4 times 4 times 4 is 64. So negative 4 times negative 4 times negative 4 is negative 64. So therefore, my answer is just negative 4. Whatever would fill in those 3 spots is your answer. A lot of you are forgetting that, yeah, once you come up with these 3 spots, you have to get rid of the cube root. I've seen in some of your homeworks and just some of your work in general that if you have a cube root here, you can't carry the cube root over. It wouldn't make any sense, right? To say that the cube root of negative 64 equals the cube root of negative 4. You need to drop the radical symbol when you simplify. Okay, and it happens more often than you would think. All right, so negative 4 is our answer for this one. Again, had the index been even, no matter what, if there's a negative under there, it's no real solution. Okay? Once we get into imaginary numbers, we'll see what those solutions actually are. Okay, we talked about, we alluded to the I idea already. Questions on this so far, on this? I'm going to go into variables in a moment. That's why I'm asking this part now. Pretty straightforward? All right, let's go quickly look at variables now. What if we had the fourth root of x to the 7th, y to the 9th, z to the 12th? X to the 7th, y to the 9th, z to the 12th. You got this one for us? Go for it.
Okay, so you would separate it to x to the 4th, y to the 4th, and z to the 4th, or z to the 12th.
Y to the...
4th, or 8th, sorry.
Yeah, go with the 8 there, good.
And then z to the 12th. And then, just x to the 3rd, y to the 1st. and
Can't
that's it.
write. Okay, x to the 3rd, y to the... Why did you pick those numbers? And you could probably see it already, obviously, and we talked about this. But again, Tori Meg, why are these numbers your choices?
Because they're all multiples of 4.
Yeah, they're multiples of 4 that are less than the current exponent, right? So if I only have 7 x's here, I can't write down x to the 8th, even though x to the 8th, 8 is a multiple of 4. But I only started with 7 of them. So I can't write down an 8 here. I can only write down 4. So what we do is we look for the largest multiple of the index that you can possibly have. So look at the index. The index is 4. Multiples of 4 are right away 4, 8, 12, 16. Well, which one is the largest one for each of these that you can take out of it? Okay, which is the largest you can take out of it? Now, what do I do with what's left over? Anything going to happen with that? Yeah, you leave it. What about what's over here on the left side?
You reduce it to x squared.
Okay. Yx squared.
No, just x, sorry.
Why just x?
Because it's to the 4th, and that's to the 4th, so you just cancel them out.
Yeah, remember the fourth root of x to the 4th is just x. Just like the third root of x to the 3rd is just x. Okay, so the 4's kind of cancel in a sense. How do you do it with the 8 though?
That's when you do for the second,
Because?
because it would be like y to the 4th and y to the 4th. So you just, those are both different y's, so you just smash them together.
Or y to the second, y to the second, y to the second, y to the second,
Yeah.
which is what you meant really.
Yeah.
Okay. How about the z?
And then the z would be z to the 3rd.
Good. All times the fourth root of x cubed y. Let's quickly just reiterate what Tori May was just saying. Okay? What she said was this. The x term that we see here is x because this was x to the 4th, and we have the fourth root. What was the conjecture that we came up with? We take the exponent and... Good. Take the exponent and divide it by the index. So this 8 divided by this 4 is what gives us this 2. This 12 here divided by this 4 is what gives us this 3 down here. Okay, and we went over where that comes from in class, but you can continue to use that conjecture. You don't need to go through all the work every time. That's the idea, that once you prove something or show yourself something, then you can use that knowledge to help expedite the problem, right? Help go through the problem a little quicker. You could write this out a few times, sure, and you could write it out that this is really, right, this is really z to the 3rd, z to the 3rd, z to the 3rd, z to the 3rd, right, 4 times, which is why this is z to the 3rd. This y to the 8th is really y squared, y squared, y squared, y squared, 4 times. That's where the y squared comes about, etc., etc. But there's no need to do that all over again. Okay, we did that in class already, so just go ahead and take your exponent and divide it by your index. Now remember that for this to work, the exponent needs to be a multiple of the index, which is why Tori May brought those out in the very beginning. Please remember when you're writing out your index, that your index appears right above the radical and not over here. See how this 4 is right here? Had this just been z, and if you put your 4 like right here, I'm not going to know if it's a fourth root or z to the 4th. You follow what I'm saying? When in doubt, just do this. to make it obvious. If your handwriting is at all difficult to read. What else? I think that was it for 6.1 that we did. 6.2, we started to break up some of those. This is not going to help. I'm thinking that the sound is going to stop. That's outside. It's just when it gets loud, I naturally just close the door thinking it'll make it better, but not when it's outside. All right, so 6.2. My last name is plural now? How old? 6.2, we talked about breaking up our radicals, right, into its components. So if we have something like the following, and let's combine 6.2 and 6.3 because they're really the same entity, these sections. So what if we had something like this? Because this involves breaking it up and adding and subtracting at the same time. What if we had something like this? What's the first step? Yeah, what do you got?
Square root of 25 square root of 3
Okay.
plus square root of 16 square root of 3.
And notice, when you're adding just simply two terms together, there's a good chance that you'll get the same radicand left over, right? So that they're like terms, or else they wouldn't be able to add together. If I, instead of choosing 16 and 3, had tried to choose 4 and 12 and left the 12 without breaking that up further, I'd end up with a 12 and a root 3, and you can't add those together. They're not like radicals, just like variables. But the root 3 appears twice, which is convenient. Okay, which is convenient. What does root 25 reduce to? Everybody. Yeah, so 5 root 3 plus?
4 root 3.
Which is how many root 3s?
9 root 3.
Yeah, remember, think of root 3 as a variable like x. Had this been root 3, and let's say, hypothetically speaking, this had been root 2, it'd be like saying x and y. If you have 5x plus 4y, you can't add them together. They're not like terms. So if the radicals aren't the same, you can't add them together. Arthur.
So when you're multiplying them, if they were the same, would it still be 3 or would it be 9?
It would be 9. Because when you multiply the insides and you multiply the outsides. Just like variables. If you had 5x times 3x, isn't it 15x squared? You multiply the x's, you would multiply the 3's. Does everybody see the question he's asking? Had this been multiplication instead, we could do the exact same problem. Make believe it wasn't adding. Okay, you would have to multiply the outsides, giving you 20 now. And then it would be radical 9, which is really just 3. So it would be 20 times root 9, which is just 60. Okay, had it been multiplication. Remember, for multiplication, outsides multiply outsides, insides multiply insides.
So if they were different, you could still multiply them?
Absolutely. So multiplication, just like if I have 3x times 5y, it's 15xy. You technically multiply the xy, they just read them separately. When they're numbers, though, had this been 5 root 3 times 4 root 2, it would become 20 root 8. 20 root 6. Jeez. 20 root 6.
No, you don't have to. Since it's multiplication, could you combine 75 and 48?
By multiplying them? You could, but that would be messy, right? Yeah. So that's why we simplify first. But you could, absolutely. You could do 75 times 48 and then try and break that down into perfect squares. You would factor out a 400 out of there.
Okay, I wouldn't do that.
Do 75 times 48 and then divide it by 400. 400 would come out. But that'd be a mess, right? You know how I knew it was 400 that factors out?
20.
Yeah. Because in the end, you'd get 20, right? What's the square root of 400? 20. That's the only reason I knew it, 400. But yeah, you wouldn't do that. You'd break it down first.
But there was like a question on the problem set, and it was like one of the radicals couldn't be like broken down.
You leave it separate. It can't be added together.
And then
Addition,
if
right?
you could break down the other one, you would multiply them? You would multiply them first and then break them down? Like it was like, I forget what it was. But
So like, for example, like if you had
I
like
remember.
radical 8 times radical 6, you could break down the 8 into 4 and 2,
Yeah.
or you could just multiply them first. In this case, it doesn't matter because it's such a small number. So if you want to write this as root 48 and then break that into 16 times 3, that's fine. But if you did it the other way, it'd become like this. Right? That's what you would have. This would be 2 times root 12, but then root 12 would be broken up into 4 and 3, right? So this would become 2, root 4, root 3. This is really 2, which gives you 4 root 3. Same answer as if you had done in the beginning, writing it like this. Break that into 16 and 3, becoming 4 root 3. Okay, same answer either way, but it doesn't matter in that kind of a problem. Okay, but there are certain situations where you don't want to multiply the radicands because it's going to get messy. Okay, the number is going to become too large to want to break down. Let's do ones where we have to rationalize a denominator in the process. Okay, rationalization. So let's say we have
Is it still 6, 2, and 6?
still 6, 2, 6, 3, yeah. The last part, 6, 4, was the binomial denominators and binomial multiplications. So what if we had radical 8x to the third over radical the perfect square multiplied by radical 5 x. Radical 5x. Okay? All right. What would I do? What would I do for this problem? Worth, give me a starting point.
Well, okay, thank you. Could you make that just one big radical? And then
Yeah, I would start with that because why?
Because then you could cross out one of the x's.
So a lot of people might be tempted to multiply by root 5x over root 5x right away. And I can see why you would do that, right? Because root 5x is in the bottom, and you want to get this to become 25x squared, so you multiply by radical 5x over radical 5x. But if you think of it as a fraction and as a whole first, you could see that one of these cancels with this, right? So you could start by reducing and just make this a 2 and go ahead and get rid of this one. And that makes the problem a whole lot easier on you. A whole lot easier. Because now the numerator, we could take the square root of x squared, which is the absolute value of x, times root 8 over root 5. That's what we have left now. Again, this is x squared here that can come out as absolute value of x over root 8, or times root 8 over root 5. And now to rationalize, how would you make the bottom a perfect square? What do you have to multiply it by to make the bottom, Francis, a perfect square? 5? Just 5? Yeah, good. Square root 5 over square root 5. Okay, let's go ahead and do that. So that makes the top okay, absolute value of x, root 40, over the bottom, which is root 25. And root 25 is clearly just 5. I'm just writing it down to show the steps. Going in like a bit of a circle here, sorry. What do I do next? What do I do next? The bottom is clearly simplifiable. What does that become?
5.
Good.
On the top, you can break down 40.
Into?
4 and 10.
Yeah, there you go. Don't forget to break down the result. Remember, that's the last step. You might simplify the denominator, and that's great. But don't forget the numerator needs to be simplified as well. Okay, so our final answer for this, what do we get for our final answer for this one?
This looks
2 absolute value x. Okay. Yeah, which looks a little bit messy, but that is indeed the right answer. If 2 and 5 had any common factors, you could simplify, right? Had this been a 6 instead of a 5, you could reduce the 2 and the 6 into 1 and 3. Don't forget that at the end. Okay, if everything has the same factor, notice here these don't, but if they did, you could simply reduce them. What about things like cube roots in the denominator where we have to rationalize? Let's look. It's supposed to be a 3. Cube root of 54 x over 2y. Over 2y. Right away, you'll notice that the denominator is irrational. There's a cube root. So it's tempting to simplify right away. What should I do before I simplify though?
You can factor out from the top 8 and 7. Oh, radical.
But it's 8 times 7 is 56. You're thinking of 9 times 6 is 54. But 9 and 6 aren't perfect cubes, so that's not going to work, right? 9 is a perfect square, but we're looking for perfect cubes now, right? We're looking for perfect cubes now. Ida? Yeah, isn't 54 27 times 2? And doesn't the 2 actually end up reducing with the bottom there as well? So you could start by writing this as the cube root of 27 times 2 times x all over 2 times y. The 2's are going to cancel. What's the cube root of 27? Sorry, May? 3? You raised your hand, that's why I called you.
Yeah,
It's all right. So it becomes just 3. That comes out front. And we're left with the cube root of x over y. That's what we have right now. Still not rational, though. The 3 in the front is a coefficient, so leave it for now. But it's still not considered to be rational because of the denominator. We want to rationalize that. What do I need in the bottom in order to get rid of a radical if the radical has an index of 3?
Oh, okay, the cube root of y squared.
Yeah, you need to multiply by the cube root of y squared over the cube root of y squared. Why is that, Worth?
It's because you're trying to make it a cube so that y can, so that you can simplify y.
Yeah, very good. The denominator, you need to make it a cube. What's y times y squared? Y cubed. And you're taking a cube root. So when you're taking a cube root, you need to have something to the 3rd power, or the 6th power, or the 9th power, right? Because it's a cube root. So this would make the problem become, the 3 in the front is still there, cube root of, and now I'm going to write it as separate fractions. The numerator is just x times y squared, and the denominator is y times y squared, which is the cube root of y to the 3rd, which, as we said, is simply just y. Okay. Again, once you get y cubed down here, then you have the cube root. Those end up canceling each other, leaving behind a y in the denominator. When it comes out here, well, this 3 was in the numerator before, right? Coefficients are always in the numerator. So it becomes 3 over y. Again, the y that came out of the denominator needs to go underneath the 3 from the coefficient 3. And the xy squared from up here, x times y squared, carries itself down. Do I need to put this over 1? No, I don't. I could put that all in the numerator and then write it all over y. So another way to write this answer, right? This is good for like multiple choice problems. So if you saw this as an answer, it's the same thing. Okay? Those are the same exact things. The 3 is in the numerator, so is this entire radical. So you can put that in the numerator together and then put with the y by itself in the denominator. It's no different. What's the goal of rationalizing a denominator? What do you need to get? And generalize the statement, please. Don't just talk about perfect squares or cubes or perfect fourths. In general.
Like a real number in the denominator.
Yeah, you want to get a number that's not under a radical, or let's say like a rational number or a rational expression like y down there. If I had a 4th root, what do I want to get in my denominator so I can simplify? Something to the 4th. So if this had been a 4th root, the whole problem, make believe the whole thing had been a 4th root, when we had a y down here, we'd have to multiply by y to the 3rd over here instead. And then that would give me a y to the 4th down here, and if it was a 4th root and y to the 4th, those would reduce, giving me the y still. So whatever the index is, you need that to be the exponent as well. Okay, it gets more difficult sometimes with numbers because numbers are difficult to remember your perfect squares and cubes. Okay, but if you're having trouble with that, simple things like flashcards help. So on one side of the flashcard, you might have something like 2 cubed, and on the other side you have 8, then you have 3 cubed, and you have 27, 4 cubed, 64. Okay, you could even do things to the 4th power, but I'm not going to, you don't need to memorize all the stuff to the 4th, okay? You have calculators though. So please utilize them if you need them to see what your powers are at certain points. Okay, use your calculators as you can.
On your calculator, can you see, like, if you want to see what the cube root of a number is? Like, how do
Yeah,
you
you could press, this is something you didn't learn yet, but you could press the number and then press caret, like power, parentheses, 1/3 power. A 1/3 power is the same thing as a cube root. A 1/4 power is the same thing as a fourth root. A 1/2 power is the same thing as a square root. But the power needs to be in parentheses. It needs to be. Try 25 caret 1/2. Put the 1/2 in parentheses though. You'll get 5.
How much points is it?
Total of 75. 75 points.
What's the like,
Format's going to be 2 multiple choice only. It's not going to be a lot. Then from there, it's going to be pretty much all short answer. And then the last problem, I'm going to ask you to, and I'll give you a hint on the last one. I'll give you a hint right now. Because it was one of the ones that you did in your problem set, but nobody's asked me a question on it yet. So I'm not sure if people didn't understand it or just didn't get around to asking. If I told you that g of x equaled, let's say x plus 2 over x, and I asked you to find g of radical 2 plus 3, something like that. Okay, this was in your problem set. It was also in your one of the homework problems. Okay, you need to remember to take radical 2 plus 3 and plug it in for x right here, and plug it in for x in the bottom. And then also don't forget to add this 2 down here. Okay, and the reason you'd be asked this problem, what would you be responsible for doing after you simplify it? Because that's easy to simplify, right? That becomes a plus 5 in the top. But what do you still need to do? Yeah, so let's go ahead and finish this one. You guys give me another second. I know that it's the last period, so give me another second. This becomes root 2 plus 5 over root 2 plus 3. And from yesterday's lesson, how would I rationalize this one? Liam? The conjugate. The binomial conjugate of the denominator, which in this case would be
Root 2 minus 3.
over.
Root 2 minus 3.
Okay, and what do we notice in the denominator, folks?
Root 2, that's opposite of, things.
Difference of?
Perfect square.
Yeah. So in the denominator, when I multiply, when I remember that I need to do this in both the top and the top I need to FOIL out. That's going to give me root 4. Outer is going to give me minus 3 root 2. Inner is plus 5 root 2. And then last is going to give me minus 15. It's a minus sign, minus 15. The denominator, though, notice the middle terms cancel. You're going to get root 4. Outer is going to be minus 3 root 2. Inner is plus 3 root 2, so you don't have to do them. Just do the 3 times negative 3, giving it minus 9. So the denominator just becomes 2 minus 9. The numerator becomes 2 plus 2 root 2 minus 15. This then simplifies the numerator to be negative 13, right? 2 minus 15 is negative 13 plus 2 root 2 all over negative 7. Okay, now one last thing to point out. Had the 13, the 2, and the 7 all had a common factor, you could reduce. So had these all been even, you could reduce by a factor of 2. Okay? Make sure you study tonight. What else to do tomorrow? 6-4 is due tomorrow. I never checked 6-3. I never checked that, so make sure you bring that tomorrow also. Bring 6-3 and 6-4.